Before a single piece of hardware fails, a network is usually compromised by a single word used incorrectly in a boardroom. Look at these 4 terms: vulnerability, threat, risk, exploit. If you had 5 seconds to give a distinct definition for each, could you do it? Most technical professionals conflate them, and this specific semantic overlap is a primary reason experienced engineers fail advanced governance exams like the CISSP. In daily IT operations, using threat and risk interchangeably rarely stops a server from rebooting. But in security architecture, blending these variables results in logically flawed system designs that cannot pass a professional audit. Advanced security frameworks do not test your technical memory. They test your strict semantic precision. Small words change entire operational meanings. To bridge this gap, we will construct the complete mathematical ontology of information security risk, working from first principles. In security leadership, precision in terminology is the foundational requirement for precision in engineering. Let's build the model. We begin this diagram at the absolute baseline of all security architecture, an asset. Let's use a bank database as our example. An asset is anything requiring protection because it possesses measurable value to the organization. If a system has no value, it has no place in the risk model. Next, we introduce the external variable, a threat. A threat is the specific who or what that executes an attack, like a hacker or a strain of malware. Notice that while the threat sits outside a strong perimeter, it cannot cause damage. It exists, but it remains isolated. Now we introduce the internal variable, a vulnerability. This is an inherent structural flaw within the system itself, such as a weak password or an unpatched server. This establishes a critical architectural rule. A vulnerability purely defines a weakness. Without an active threat attempting to breach it, the vulnerability is not an immediate risk. It is just a structural flaw sitting dormant. The catalyst that bridges this gap is the exploit. The exploit is the how. It is the specific mechanism or technique, like a brute force attack, used to bypass the flaw. It represents the active execution phase of the attack vector. When that vector successfully strikes the asset, we reach the final state, risk. This is the exact intersection of attack probability and business impact, such as a realized data breach. Risk only materializes at the precise moment a specific threat successfully leverages a specific vulnerability against an asset. Because this state depends on all these components, removing any single variable from the system causes the risk to cease to exist. Without the threat or the vulnerability, the equation cannot be completed. With risk measured, we can now categorize our defenses by their functional roles. Security controls must be evaluated against a rigid chronological timeline of an attack, moving from left to right. The first chronological phase occurs here, before the physical event takes place. These are preventative controls. Their singular functional intent is to reduce the likelihood of an attack reaching the asset. Firewalls and data encryption sit in this category.
If the perimeter fails, we enter the second phase, actions taken during or immediately after the breach. These are detective controls. They do not stop attacks. Their sole functional purpose is to observe, identify, and alert administrators that an exploit is occurring. CM logs and intrusion detection systems operate here. The final phase occurs after the asset has been compromised and the risk has fully materialized. These are corrective controls. Their intent is to restore the system back to its baseline operational state post-incident. Think patch updates and full system restores. You can eliminate half the incorrect options on an exam simply by matching the verb in the scenario. If the goal is to reduce likelihood, the answer is preventative. If it's to identify, it's detective. To restore is corrective. Security controls are categorized by their chronological intent. They are never categorized by their underlying technology. A firewall or a CM tool cannot exist in a vacuum. Technical controls must be legally mandated by organizational governance. That governance follows a strict, non-negotiable documentation hierarchy represented by this three-tiered blueprint. It flows from broad executive mandates down to individual keystrokes. The highest tier is the policy. This is the overarching, mandatory directive from executive leadership. A policy defines what must be achieved. For example, a policy states passwords must be strong. It explicitly avoids mentioning specific technologies, metrics, or implementation steps. The middle tier is the standard. A standard provides the mandatory, quantifiable parameters required to satisfy the policy above it. Instead of strong passwords, the standard mandates passwords must be exactly 12 characters. It represents rigid compliance metrics. The bottom tier is the procedure. Procedures are tactical, step-by-step instructions for the engineering team. This document explains exactly how to configure the Active Directory software, select the user, and force the password reset to meet the 12-character standard. Sitting outside this rigid compliance structure is the outlier, the guideline. Guidelines are recommended best practices. Because they are optional, auditors cannot use guidelines to enforce compliance. Mixing these tiers, like putting specific Active Directory commands into a high-level executive policy, weakens the framework and often results in audit findings. These documents must remain functionally distinct. When we connect these three frameworks, we get a single architectural system wrapped in business context. Mastery of this system divides tactical operators from strategic architects. The decision flow is absolute. Business impact dictates risk. Risk dictates governance, and governance dictates technology. Never evaluate a technical vulnerability or a control mechanism in isolation. You must trace it upward through this model to its direct impact on business operations. Advanced certifications are not a test of how hard you can study. They are a test of how sharply you can think. Master the precision of these terms, and the precision of your engineering will naturally follow.